Yeah, first of all, I'd like to thank the organizers of the workshop for giving me the opportunity to present my work here in Jerusalem. So for those that I haven't met yet, I'm Clément Bonnerot. I'm a PhD student at Leiden Observatory, working with Elena Rossi and Giuseppe Lodato. Unfortunately, they couldn't come to this workshop. And today, in this talk, I'd like to give our contribution to the open question of disk formation that has already been discussed in the two first talks. And then in the last slide, I will just give an advertisement about the work that is done on a different subject and will be on the archive tomorrow. So just to come back to the basic description of a tidal disruption, it happens when a star, after a succession of encounters with surrounding stars, is scattered onto an orbit that is parabolic, so with eccentricity 1, and that enters the tidal radius of the black hole, meaning that the penetration factor defined as the ratio of the tidal radius to percent distance is larger than 1. And as we heard yesterday from Rem, what happens during the disruption is that the debris will get a spread of orbits, with half of them getting bound to the black hole, while the other half is unbound and escapes on hyperbolic orbits. And then the question of disk formation is the following. How do you get from this very eccentric and energetic stream of gas and remove enough orbital energy from it so that it forms an accretion disk on circular orbits close to the black hole? And this question is important because it's from this accretion disk that comes important electromagnetic signatures of tidal disruptions, such as the thermal flare that is due to accretion within the disk, and possibly relativistic jets that are launched in the inner regions of this disk. So the question that I like to answer is first, what the mechanism for disk formation? And it has been mentioned previously in the two first talks that a way of doing that is through apsidal precession that leads the first debris to fall back towards the black hole to precess and to collide with the part that is still infalling. And this leads to formation of shocks that remove orbital energy. Then another question I'd like to answer is on what timescale does the disk form if it forms? And also what's the structure of this disk? And this is also important because we've heard yesterday that the extension of the disk can lead to different blackbody temperatures detected from this disk. And finally, I will just touch this final point of the accretion within the disk, and more specifically by which, what is the rate of accretion within this disk, and is it set by the fallback rate of the debris or by some other rate? Okay, so ideally, the initial condition of such a simulation would be this one. However, as has been mentioned in the first talk, this is very computationally expensive. For the two standard parameters, so an orbit of the star of 1 and the mass ratio between black hole and star of 1 million. And an intuitive way to understand why it's computationally expensive is to say that the stream that is produced for these two parameters is very extended, so that is very expensive to resolve the different part of this stream. And so there are two possible ways of going around this problem, either by decreasing the eccentricity of the star artificially, which makes all the debris more bound, and therefore the stream is shorter and less easily resolvable, more easily resolvable. And this has been used in the previous talk, while another way to go around this problem is instead to decrease the mass ratio between black hole and star. And this has been used in the first talk by Rosanne. And here, this also solves the computational problem because although the center of mass of the stream is still on a parabolic orbit, the time for the first debris to fall back towards the black hole is shortened, so that the stream has less time to extend. Okay, so the simulation that we did is using an SPH code called Phantom, doing both the disruption of the star on a bound orbit around the non-rotating black hole, and then follow the fallback of the debris where disk formation takes place. And now there are three characteristics of this simulation that I want to highlight. The first is that we're using a relativistic potential that reproduces exactly the rate of apsidal precession. And so in this sense, our simulation is as accurate as a full GR simulation, but they are also cheaper, which allows us to probe a larger parameter space. And the second aspect that I want to highlight is that we are starting from highly eccentric stars up to an eccentricity of 0.95, which is close to the standard case of a parabolic orbit and will allow us to get insight into this standard case. And finally, as in the previous talk, we are using two extreme cooling efficiencies, either very efficient cooling encoded in a either thermal equation of state or a very inefficient cooling encoded in adiabatic equation of state. Okay, so first I will show the results of those simulations with movies. Starting from a fixed stellar orbit of an eccentricity of 0.8 and penetration factor of 5, which means that the per-center distance is 5 times smaller than the tidal radius. And in this case, the apsidal precession angle is very high, is of order 90 degrees. And this you will see in the movies. So first I will begin by using an efficient cooling. In this case, this is the gas and this is the black hole. As you can see, the gas precesses around the black hole, and at this point, this leads the stream to collide with itself, which transfers kinetic energy into thermal energy. But the assumption that is made here is that this thermal energy is radiated away very fast, that the net effect of these shocks is just to decrease the orbital energy of the gas. And this, after a circularization timescale of about 5 times the period of the star, leads to the formation of this thin ring that is located around the circularization radius, shown as the dashed circle. Okay, so in this case, a thin ring forms at the circularization radius with a circularization timescale about 5 times the dynamical timescale of the debris. And here we find that there is only negligible ballistic accretion onto the black hole. And another thing that can be derived is what the thermal energy that is released during this disk formation. And in this case, it's just given by the difference in orbital between the initial orbital energy of the stream and the final orbital energy, which is the circularization energy. In this case, it gives about 10 to the 52 erg. Okay, now just to check whether apsidal precession is actually what drives circularization, I did the same simulation, but instead using a Keplerian potential. And in this case, as expected, there's no apsidal precession, therefore no intersection of the stream with itself, no shocks, and no energy loss from the gas. And so at the end of this simulation, there's the formation of this eccentric strip of gas that is way well outside the circularization radius. Okay, and finally, what I want to show is still using. Oops.
What is the per-center exactly used?
10.
What is the per-center?
10. 10.
Okay.
And now, if I change the cooling efficiency to large cooling efficiency to inefficient cooling. Initially, what happens is similar to the previous case, but when the shock occurs due to self-intersection of the stream, the thermal energy, instead of being radiated away as before, is kept inside the gas, which leads to the formation of this thick and extended torus instead of a thin ring in the case of an efficient cooling. And this torus forms on about the same circularization timescale as before, and it's located between the circularization radius, which you will see here, and it's within the semi-major axis of the star. Okay, so in this case, what we can learn from that is that the efficiency of the cooling determines what's the structure of the disk, and this disk is thicker and more extended for an efficient cooling. And what is also interesting is that in this case, we find that there is about 20% of ballistic accretion onto the black hole. And now if we do the same game as here, computing what's the thermal energy in the torus at the end of our simulation, we find that it's only 10% this, let's say, maximal thermal energy, which would give 10 to the 51 erg.
Just one quick question. Does your pseudo-Newtonian potential have the right ISCO for measuring ballistic accretion?
We are fixing the ISCO at the
Oh, you're just putting it in. Okay.
6 RG.
Is any form of viscosity included in this code, or
So there's artificial viscosity, which is used
just
to
for shock, but not for
resolve the shock.
shear viscosity?
But then there's a switch that switch off artificial viscosity when there are no shocks. So when the disk forms, this switch is active, so there's no viscosity.
And shear viscosity, any shear viscosity that is added.
No.
So this is SPH, right?
Yes.
So SPH is intrinsic viscosity which is very low.
Okay, you mean artificial viscosity?
You can call it artificial, it's numerical. It's big in the skin, there's a lot of this SPH skin induces a lot of viscosity.
Okay.
Another way to put that is, what's your smoothing length?
Here we're using 500,000 particles, but the smoothing length, well, it depends on the density of the gas. So it's
Right,
difficult
so
to
how many
say.
particles per volume?
Here it's using 500,000
No,
particles.
per smoothing volume, exactly. Using an SPH, there's always an averaging.
Mhm.
And the question is how
And the
much-
number of neighbors, you mean?
No,
it's
when you calculate both pressure and density, you're averaging over some number of particles, which is
I think it's 58 particles. Okay, just to continue, I'd like to continue on getting more giving more information on the structure of this torus. So as I already said, it forms between the semi-major axis of the star, which is 1 here, and the circularization radius, which is 2/5 here. And another important thing is that there is centrifugal support in this torus only in the inner regions. And also the pressure support in all the torus is only of order 10%. And combined with the fact that we find that 91% of the gas stays bound, which is the majority of the gas, it means that this torus is not in equilibrium, and that this outer region is likely to, at later time, fall back towards the inner region, which could lead to shocks and possibly more emission. Okay, so now, so far I just considered one orbit for the star. I'd like to change this orbit, keeping the assumption of efficient cooling. And I'd like to change this orbit in 2 ways. First, by increasing its eccentricity, keeping the penetration factor fixed, and then by increasing instead this penetration factor, or decreasing the penetration factor, meaning increasing the pericenter distance. So what happens in the first case? Just like to pause here to say that this is likely to be similar to the case of a parabolic orbit for the star, because this is the highest eccentricity that we considered. And also the pericenter distance is unchanged, which means that the apsidal precession is still high, about the 90 degrees. And the combination of these two facts implies that the stream collides very early. It doesn't have to chase itself like in the previous case to collide. And this leads to disk formation that is faster than in the previous case of order of the dynamical time of the debris, so of about 1 times the period of the star. And now if I do the other game of increasing the penetration, the pericenter distance, here instead the apsidal precession angle is changed, and it decreased from about 90 degrees to 10 degrees. And this leads to shocks that happens further from the black hole, where relative velocities between the two components of the shocks is lower, and so therefore these shocks are weaker and less efficient at removing orbital energy from the gas. So again, a disk forms, which is a thin ring around the circularization radius, but this disk formation is slower than in the previous case. Okay, so that's the
If the semi-major axis for both, what is the difference, the ratio between the two?
this is 4. This is 500 solar radii and 400 solar radii.
So the left is closer.
Well, in terms of semi-major axis, yes, but in terms of percent, this one is closer. Okay, so that another conclusion of our work, which is in the case of bound orbit. In the case of bound orbits, the circularization timescale is determined by the stellar orbit, being shorter in the case of larger eccentricity and longer in the case of larger percenter. And now I would like to maybe get more speculative on in trying to understand to what extent these results can be extrapolated to the case of parabolic orbit. And what I will say, if I come back there, is that the main difference between this case of a bound orbit and the case of a parabolic orbit is that in the case of parabolic orbit, instead of having all the debris involved in the disk formation, there is a long stream of gas here and only its tip is involved in the disk formation. However, if we keep the penetration factor or percent distance fixed, this epsilon precision will stay large, leading to shocks close to percenter, which will drive the disk formation in a dynamical timescale. And so one way to extrapolate these results in this case for large penetration factor is to say that due to shocks that happen still at percenter, the circularization timescale is about the dynamical timescale of the most bound debris, because those are the ones involved in circularization in this case. However, for the case of beta equal 1, this is much less clear because, as I showed you here, due to the slow apsidal precession, the shock happen at apocenter of this debris, so they are weaker. But it's even worse in the case of a parabolic orbit because the apocenter of the most bound debris is even further than in the case of the bound orbit that we considered by a factor of about 2. So in this case, the circularization timescale is likely to be much longer than this. So maybe a few tenths of Tmin. Or another possibility is that instead of forming a disk at the circularization radius, it forms an elliptic disk, and that will be discussed in the talk, in the next talk. How much do I have left?
More or less done.
Okay, I'll switch this. So yeah, I'd like to finish by advertising a work that we've done recently in investigating what's the interaction between the bound part of the stream with the gas surrounding quiescent black holes. And what we found is that Kelvin-Helmholtz instability, which is a sharing instability between the stream and the ambient gas, can in some case lead to the dissolution of this stream into the ambient medium. And this effect is enhanced if the density contrast between these two components is decreased, which occurs both for massive black holes and for giant stars. And so previously it has been argued that above 10 to the 8 solar masses, where mean sequence stars are destroyed within the Schwarzschild radius of the black hole, leading to no substantial emission. Above this black hole mass, the black hole diode would change from main sequence stars to giant stars. But instead here we argued that as these two conditions are satisfied in this region, all these events involving both giant stars and massive black holes would be much more difficult to detect than expected due to this Kelvin-Helmholtz instability. So I would be happy to discuss this later. Thank you for your attention. The main physical difference. Oh, there's. Yeah. So in this case, we found that there is a slight dependence on the resolution of the simulation. You use the 1000 than 100,000 particles, and we use 500,000 particles. And we found that this quantitatively is similar. Yeah, there's this formation occurs maybe in it requires one more evolution to circularize when the resolution is increased. And we find that this is actually converged result. Yes.
So there's a paper by Kaplan and Dixon, maybe past couple months, that proposed that there's clumping in the stream that leaves variacs due to a gravitational instability. Do you see any evidence of clumping in your simulation?
We are not considering, we are just using a simple analytical model which treats only Kelvin element instability.
Oh no, I mean your SPH calculation. Do you see
Oh.
any evidence of clumping in the SPH calculation?
No. That's the short answer.
Self-gravity and I think clumping.
Yeah, so self-gravity is so something that I didn't say is that we include self-gravity only when we study the disruption of the star. And when the first debris falls back towards the black hole, we're just switching off self-gravity.
Oh, you switched off entirely.
Yes.
If you wait until the first return, that's study long enough to see the clumping Kaplan and Alice thing, because that's right after the disruption process.
But I don't know when you're turning off self-gravity. When are you turning it off exactly?
It's because it's computationally faster.
When?
When? So basically, in the simulation that I showed, self-gravity is turned off.
What time?
When the first debris reaches the black hole.
So when that reaches variac, that's when you switch off gravity.
Yes,
Self-gravity
yes.
at that point. Okay. So
But
there
it-
should be clumping principle.
But in our case, I think the main difference between the work of Nixon is that we're using bound orbits, and the material takes much less time to come back to Paris center, and so self-gravity, I think the clumping in this case is less likely to happen.
But on the other hand, the linear mass thing is not with the decrease in stability.
Their latest paper suggests that there's some transition right around gamma of 5/3 where it goes from clumping to not clumping. But if you guys don't see it, then likely that something else going on.
Okay, last question.
Did you share
That's a good question, and we didn't check that. But I think what you mentioned is that the main effect of magnetic field, if I understood correctly, is to change the balance of forces in the transverse direction. And does it also change the dynamics in the longitudinal direction?
You have field lines that are oriented parallel, like with the stream itself. I think the question of the KD as the typical configuration of the field, right? The changes there are where the field lines are parallel to the intersection of the KD. But you do have background magnetic fields too, right? That also plays a role in the KD stability.
Okay.
Okay, thank you very much.